Hello everyone, how's it going? My name is Dan the Tutor, on a mission to become the world's greatest tutor. In today's video, we have a fun one. It's the banked curve example. So this is a very famous problem in physics, where you have some kind of banked curve like this, and we have a car driving on the road like that. The ramp has some angle theta, and the reason why the road is banked is because it allows you to take the turn at faster speeds. That's why if you ever watch NASCAR, which I don't know why you would, but if you do, you'll notice most of the track is curved. And that's because it allows you to have gravity work in your favor to help you make the turn, and so therefore you can go at higher speeds. Now in this problem, I want to know the max speed that this car can take, given that there's no friction. The mass of the car is unknown. We have angle of the ramp theta, and this turn has a radius r, capital R. So in other words, if I were to view this car from a top view, like a bird's eye view, you wouldn't be able to see the banked curve from this perspective, but I'm saying it has a radius to the center of capital R. And I want my answer all in terms of variables, at least theta and r. Those are the only two I give you. So how are we going to solve this? So this is a very famous physics problem because it's extremely difficult. As a matter of fact, I say this is one of the 3 physics god problems, the 3 hardest problems in physics. And if you watch enough of my videos, you know what the other 2 are. But here's how we're going to solve this. First, we start off with a free body diagram, but we have to decide if we want to do the front view or the top view. And my recommendation is do the front view. We're going to be able to see more forces going on here. So I'm going to redraw it down here. And so for this car, we have a gravity force going straight down, which I'll call mg, and a normal force going up and to the right, which I'll call Fn. And that's it. There's only 2 forces going on here. I know that doesn't seem like a lot, but the only other force would be friction, and we said there is no friction. By the way, if we did have friction, friction can technically be going either way, either up the ramp or down the ramp. Just to explain that really quickly, because sometimes there is friction in these problems. You have this friction pointing that way if you're going too slow, and friction will be pointing this way if you're going too fast. The reason why is because friction always wants to oppose motion. If your car's going too slow, it's going to go towards the middle of the curve. It's falling down. And if you're going too fast, it means that you're flying off the edge of the embankment. If you don't know what I mean by that, just think about it for a couple minutes. I think it will make sense as it sinks in. But regardless, I don't have friction here, so let me erase all of that. Now, one thing you've heard me say before in other videos is that whenever you have a ramp problem, always rotate the diagram. And technically, that's not true. The reason why we were rotating the diagram is because the acceleration always pointed up or down the ramp. But for this problem, the acceleration does not point up or down the ramp because we do not want to move up or down. We want to stay in place. So then, is the acceleration 0? And no, it's not going to be 0. And the reason why, we can see it from the top view. There is an acceleration here. It's a centripetal acceleration, AC. And that acceleration does not point down the ramp, but instead it points straight to the right. I know it doesn't really make sense from this perspective, but again, if you look at it from this perspective, at least the acceleration does make sense. It needs to point towards the middle. And remember, acceleration should not be going on your free body diagram. That's why I'm drawing it off to the side a little bit in a different color to emphasize that. It's not going on my free body diagram. But what this does mean is that if I rotate the ramp, I'm not going to be happy. Why not? Because acceleration already points in the x direction. And there's no y direction. You can say ay equals 0. So I actually don't want to rotate the ramp here for that reason. But then what does that mean? Because normally I would be breaking up mg into x and y components. Well, I guess now we're going to be breaking up Fn, normal force, into its x and y components. But then that begs the question, how am I going to draw a triangle for the normal force, right? Because theta's way down here. How am I going to draw a triangle for that? So there is a proof to find it, and to help us, I'm going to replace the car with just a dot. normal force is still pointing that way, and theta is still right down there. If I make a mini right triangle right there, then I know that this angle that I just made up is also going to be theta because they're alternate interior angles. Which then means that this angle here, since they're complementary, theta and the black one I just drew, that's going to be 90 minus theta. So in other words, there's two triangles I can draw here. One where normal force is there, and here's x and y, and the angle right here, again, is 90 minus theta. Or I can draw this right triangle between the imaginary vertical line, and the reason why I would do that is because now this angle is theta again because of the complementary angle rule. And so then I can have this blue triangle where FN's the hypotenuse, and this is my angle theta. And so it's up to you which triangle you want to do. Personally, I like to do the blue one. I also go with the blue one like immediately. Like I never prove that theta every single time, because once I know it once, I don't need to prove it again. I can just make an imaginary vertical line, put theta there, and there's my blue triangle. I usually just do that in one step. But then now, of course, we got to find the x and y components. So in this case, if I want to find the x component, it is going to be sine of theta. Why? Because sine is opposite over hypotenuse, and I know opposite is x, and my hypotenuse is Fn. Meaning, if I multiply both sides by the normal force, Fn, then x is going to equal Fn sine theta. And then for y, that's basically going to be the same thing except for cosine, because cosine theta equals adjacent over hypotenuse, and the adjacent leg is y. So y over Fn, and again multiply both sides by Fn, and there. I have my x and y components. The reason why I do this is because now I'm going to redraw my free body diagram with the car, and mg still points down, but now I have normal force y pointing up, Fn cosine theta, and another force, the x component, being Fn sine theta. And so there, step 1 and step 1.5 are done. I have my free body diagram, I split into components, and now I'm ready to go into step 2, which is Newton's second law. So for Newton's second law, you have to choose if you want to do the y direction or the x direction. For this problem, we end up needing both, but here's one thing I want to correct myself on. Normally we do f net x and f net y, but in this case there's no f net x, and that's because one of the rules for centripetal motion is that wherever you're moving in a circle, in this case the x direction, and the reason why is, if I go back up here, right here, remember we said centripetal points to the right. In other words, x is gone and has been replaced by AC. And so for that reason, I'm going to replace f net x with f net c centripetal, which is equal to all the forces pointing inward, that's going to be Fn sine theta, and then minus all the forces pointing outward, which in this case there are none. There'd have to be a force pointing that way, which there's not, thank goodness. So Fn sine theta minus 0, no forces pointing outward, equals ma, where this is centripetal acceleration, remember? So that means it's actually mv squared over r. Now I'll admit, I don't know m. I know r is, I guess, capital R. I'll rewrite that. V, velocity, is what I'm solving for. That's the maximum speed I can take this turn. Normal force I don't know, but theta is okay. So in other words, if I knew the normal force and I knew the mass, I could do some algebra, I could solve for velocity. But I can't yet because there's two variables I don't know. And luckily, there's another equation. And of course, that's going to be F net y, which is all the forces going up minus the forces going down equals ma. If I look at this picture, there's only one force going up and one force going down. So in other words, it's going to be Fn cosine theta minus mg equals ma. And remember, this acceleration is going to be 0. We're not moving up or down in the y direction. The car is staying perfectly level on the banked curve. And so because of that, we can say Fn cosine theta is equal to mg. And if I want to solve for Fn, for instance, which I do because I don't know it yet, I just have to divide mg by cosine theta. And so then plugging that normal force into what I was writing earlier, Fn sine theta equals mv squared over r, then we can say that mg over cosine theta times sine theta equals mv squared over r. And now I just have to do some algebra to solve for my velocity v. So that means I'm multiplying both sides by r and dividing both sides by m. So it's going to look like this. R over m times mg over cosine theta times sine theta equals v squared. Now I know we don't know mass, but I've got good news. Mass is going to cancel right here. And so that means I'm just left with r times g times sine theta, all in the numerator, and then in the denominator is cosine theta equals v squared. And then one more thing I want to show you. Sine over cosine is tangent, right? And I know you might not see that the first time you do this problem, but now that I told you, you're probably going to see it in the future. So in other words, this is equal to r times g tangent theta, which can be rewritten in any order you want. You can put the g first, you can put the tangent theta first, it doesn't matter. That equals v squared. And finally, we just have to take the square root. So the max speed we can take this turn is the radius of this curve times g, acceleration of gravity, 9.8, times the tangent of the angle of the ramp. And there we go. That's how we solve one of the most notorious problems in all of Physics 1. So that's going to do it for this video. If you have any questions, please post them in the comments. Thank you all for watching, and I'll see you in the next video. Take care, and bye-bye.